This is regarding the second episode, you can say, of the well hydraulics. Up till now, you have got certain idea and imagination regarding the depression head, okay, critical depression head, safe depression head, yield, safe yield, and the critical yield, etc. As I have told you that well is a hydraulic structure and which supplies the water. It is a source of the water that can be taken out from the aquifer. So therefore we need to give a technical attention towards the well. So if this well may be a open well or may be a bore well, it is a hydraulic structure, and if it is properly designed and penetrated or constructed, it gives us or it permits us economical withdrawal of the water from the aquifer. ये वेल को यदि हम प्रॉपर एक्सकवेट करते हैं, प्रॉपर डिजाइन करते हैं, उसका डायमीटर कितना डेप्थ जाना चाहिए वो, तो ये हमें एक इकोनॉमिकल मॉडल दे सकता है, इकोनॉमिकल ऑप्शन दे सकता है एक्विफर में से पानी यूज करने का, है ना. बिकॉज दो वी हैव वाटर अवेलेबल through our runoff, etc., but not to some villages or to some cities. We could not get water from the runoff, or we could not get the water from the dam or the canal. So therefore we are dependent on the wells. So therefore it is better to study the fluid mechanics or hydraulics of the well. On my every slide you will be seeing some 2-3 figures like this one. I will explain you what this figure is so that you will be able to understand what I will be teaching you in slides to come. This is a ground level. At the top you may be seeing. Through this ground level, this is a well, maybe a open well or maybe a bore well. Okay, maybe this is shown in unconfined aquifer. This well is shown in unconfined aquifer, but there such types of the well may be in confined aquifer, that we'll be trying to learn later on. Okay, so this is the well. This is the original water table, top below the ground level, original water table. On the left side there are two sample wells, you can say imaginary wells, to understand the concept. The two wells are there, very small wells on the left side. One well is at a distance of radius r1 from the center of the main well, r1 you can see here, which has the depth of water h1 into the unconfined aquifer. Okay, h1 you can say, you can see here h1. S1 is the depression head, you can say, S1 of the well, which is at a radius of r1. There is another well. Again, these are the just imaginary or the sample wells for certain derivation. वो बाद में आपको बताऊंगा ही मैं फिर से, लेकिन अभी आप समझ लीजिए, यानी आगे में आपको समझते जाएगा कि भाई ये फिगर यानी क्या चीज है. तो ये जो दूसरी वेल है, इट इज एट ए डिस्टेंस ऑफ रेडियस r2 from the main well, and this radius which is well which is at a distance of R2 has got the water depth of H2. Okay, so R2 well is near to the main well and R1 well is away from the main well. These are the three things first I wanted to bring to your notice. Okay, what is this that I will be discussing? Cone of depression, etc. Will be discussing in our next slide. Okay, now we are moving to what I have told just now. When the water is pumped out from the well, ये जो वेल है, ये वेल में से यदि हम पानी निकालते हैं, pumped out, तो पंपिंग से पानी बाहर निकालते हैं, the water table as you all know corresponds to the unconfined aquifer. So therefore the words are here, the water table or the piezometric surface in case of the confined aquifer. Water table for the unconfined aquifer and the piezometric surface in case of the confined aquifer. तो क्या होगा, ये वेल में से जब हम पानी निकालेंगे, पंप करेंगे, तो नेचुरली ये वेल का वाटर लेवल नीचे जाएगा. तो ये वाटर लेवल जैसे नीचे जाएगा, तो वैसे ही द एडजेसेंट वाटर टेबल, यानी ये वेल को लग के जो वाटर टेबल है या पिज़ोमेट्रिक सरफेस है, ये भी इसके साथ में नीचे आएगा. एंड एज वी मूव अवे फ्रॉम द वेल, जैसे हम वेल से दूर दूर जाते हैं, तो वैसे वैसे ये दिस वाटर टेबल विच हैज कम डाउन ड्यू टू द पंपिंग ऑफ वाटर इनटू द वेल or in the well will come to its original position after some distance, है ना. ये जो ग्राउंड वाटर टेबल जो इनिशियली डॉटेड लाइन में ऊपर में था, पानी निकालने के कारण क्या हो गया, वेल में की वाटर लेवल कम हो गई, उसके कारण ये वेल को लग के जो वाटर टेबल है या पिज़ोमेट्रिक सरफेस है, वो भी ये वेल के वाटर के साथ में नीचे नीचे आया. लेकिन ये वेल से जैसे जैसे हम दूर जाते हैं, वैसे वैसे ये वाटर टेबल आपको क्या दिखता है कि इट इज कमिंग टू इट्स ओरिजिनल वाटर टेबल which was there originally. Okay, if you see it in the 3 dimension as has been shown on the left side of the slide, this will look like this. If you will see from the top, यही वेल को आप यदि ऊपर से देखते हैं तो आपको ऐसा दिखेगा कि ये जैसे नियरेस्ट वेल के पास में यहाँ पे ये वाटर लेवल है वेल में की, और वाटर टेबल ये ऐसा धीरे धीरे जो है ये अपना ओरिजिनल वाटर टेबल को जा रहा है इन द फॉर्म ऑफ द कोन. ओके, फ्रॉम द टॉप यू विल सी दी वाटर. यदि आप ऊपर से देख रहे हैं तो आपको ऐसे दिखेगा कि ये जो कोन है वो कोन के शेप में ये वाटर टेबल फॉर्म हो रहा है. So the surface of the lowered water table resembles a cone and is called as the cone of depression. Okay, all of you must have imagined this concept, I think. Okay, it's very simple. As the water level goes down, what will happen around the well? पूरी वाटर जो ग्राउंड वाटर टेबल है वेल के पूरे रेडियस में आजू बाजू, वो वाटर टेबल आपको धीरे धीरे, जो वेल में वाटर टेबल नीचे चला गया है वेल लेवल को, वो धीरे धीरे जैसे जैसे वेल से आप दूर दूर जाएंगे तो वैसे वैसे ये वाटर टेबल फिर से अपने ओरिजिनल अनडिस्टर्ब्ड वाटर टेबल को टच करेगा. ऐसा दिखेगा 2 डायमेंशन में, ऐसा दिखेगा जैसे ये राइट साइड में स्केच है, और 3 डायमेंशन में ये ऐसा दिखेगा लेफ्ट साइड में है. ऐसा कोन दिखेगा ऊपर से. ये कोन को जो है ड्यू टू द फॉर्मेशन ऑफ द लोअरिंग ऑफ द सरफेस ऑफ वाटर टेबल, is called as the cone of depression. Very important concept. It is shown here in the larger dimensions so that you should be able to understand it again better. Okay, it is very simple that all this outer surface or outer part of this cone, which is circular in plan, outermost part shows the boundary of the undisturbed water table. And as we move undisturbed water table या original water table, but as we move towards the well, जैसे जैसे हम वेल के पास में आते हैं, क्योंकि वेल में से पानी पंपिंग करके निकाल रहे हैं, तो वैसे वैसे ये वाटर टेबल धीरे धीरे नीचे जाता हुआ दिखेगा आपको. और वेल के पास में तो वेल में तो बिल्कुल ही वो वेल की जो वाटर लेवल है वो वाटर लेवल को वो फ्लश करता हुआ दिखेगा. और हम यदि टॉप से देखते हैं, प्लान देखते हैं, तो हमें ये ऐसे इस टाइप से उसका शेप दिखेगा. वाटर टेबल इमेजिनरी है ये, फिर से हमें समझ लेना है कि ये द वाटर टेबल विल लुक लाइक दिस. वेल तो सिर्फ इतनी है, बीच में ही है. वेल इज इन द सेंटर, but the water table which is into the aquifer mass, into the soil mass, will take the shape of the cone, which is called as the cone of depression. To understand or to again imagine the concept, another sketch on the next slide I am showing. You can see here cone of depression, or it is also called as the cone of exhaustion. This is all the ground level. This is the well, and the water is being pumped out through the well. So naturally what will happen? All this groundwater table on all along the circular periphery of the well, all this groundwater table which is along the circular periphery of the well will go down into the in the well, and adjacent to well, as we move away from the well, this water table will try to reach its original level and it will look like a cone from the top, which is called as the cone of depression. Okay, this is all the aquifer, and this is the groundwater flow towards the well. And we wanted to understand the hydraulics of this groundwater flow. Again, the same sketch in 2 dimensions. This is the central well, main well. Adjacent to this well, there are 2 testing wells, you can say, or the virtual wells, imaginary wells, test wells भी बोल सकते हैं इनको. Now you have understood the concept of the cone of depression. Therefore, the water level into the well, which is at a distance of R2, which is at a radius of R2 from the main well, will be depressed through the height of S2. Okay, and we'll have the water depth of H2. Okay, because the water table is now slowly moving upwards. Again, if we move towards a well which is at a distance of R1, which is away from R2 or more than R2, then again the water table will be above compared to R2, and that depression head will be S1. Here it will be S2, and the corresponding water depth is equal to H1. Okay, and the last but not the least, but which is very important, at a distance of capital R, means maximum radius, capital R, this cone of depression's outer periphery or outer circle has touched to original water table. Okay, here at a distance of capital R from the center of the main well, the cone of depression has touched to the original water table, So this radius is denoted by capital R, and corresponding depth of water is denoted by capital H. Okay. So capital H is nothing but the depth of the groundwater table from the impermeable strata, or the depth of groundwater table in the unconfined aquifer, you can say, or maybe in the confined aquifer, piezometric surface. These are the things if you have understood. Now the main well, the well under observation, or whose hydraulics will be calculating, HW is the depth of water into this well, and SW is, you can say, depression head or suction head. What is it called? We'll be trying to understand in our next slide. So the horizontal distance from the center of a well to the practical limit to the cone of depression is known as the radius of influence. That is this capital R. The horizontal distance from the center of the well, that is from the center of the well to the practical limit of cone of depression, that is the outermost limit of the cone of depression, outermost circle which touches the water table, is called as the radius of influence. So capital R is the radius of influence. है ना, आप अपने नोटबुक में कहीं तो भी नोट करते रहिए। ये स्केच मैंने आपको बताया था कि ये स्केच आपके नोट्स में भी है, लेकिन हर स्लाइड पे मैंने इसलिए दिखाया है कि आप अपने नोटबुक में भी निकाल के आप समझ सके इसको, है ना। थोड़ा सा एक बार समझ लिया तो फिर ये बहुत इजी है, यानी इसके न्यूमेरिकल भी बहुत इजी है। सो कैपिटल आर इज द रेडियस ऑफ इन्फ्लुएंस। इट इज लार्जर फॉर वेल्स इन कन्फाइंड एक्वीफर्स। ये बहुत इंपॉर्टेंट स्टेटमेंट है। ये जो रेडियस ऑफ इन्फ्लुएंस है, it is more in confined aquifer than the unconfined aquifer. Okay, I think everybody has got what I mean to say. ये जो R है, कैपिटल R, जिसको रेडियस ऑफ इन्फ्लुएंस करके हम बोलते हैं, ये जो रेडियस ऑफ इन्फ्लुएंस है, ये हमारे जो वेल कन्फाइंड एक्वीफर में है, तो कन्फाइंड एक्वीफर में ये कैपिटल आर और रेडियस ऑफ इन्फ्लुएंस ज्यादा रहता है एज कंपेयर टू अनकन्फाइंड एक्वीफर। ठीक है, क्योंकि कन्फाइंड एक्वीफर में पीजोमेट्रिक हेड रहता है, वाटर अंडर प्रेशर रहता है, तो नेचुरली जो पानी यदि हम विड्रॉ करेंगे तो वाटर स्प्रेड इज मोर, देयरफॉर द रेडियस इज मोर, रेडियस ऑफ इन्फ्लुएंस इज मोर। ऑल द यदि एक्वीफर के जो आजू बाजू जितना मटेरियल है, कौन सा भी कन्फाइंड रहे या मटेरियल है ना, सॉइल, if we assume that all that soil has got the same characteristics regarding its porosity, regarding its specific yield, etc., density, that is all the variables remaining the same, the radius of influence is larger in aquifers with higher transmissivity. हमने एक ट्रांसमिसिविटी, ये एक टर्म पढ़ा है, ये मैंने नीचे में फिर से आपको रेफरेंस के लिए इमीडिएट बताया है। एक बहुत बड़ा स्टेटमेंट ऐसा है कि रेडियस ऑफ इन्फ्लुएंस और कैपिटल आर इज मोर और इज लार्जर इन एक्वीफर्स, दैट इज we have seen earlier that the confined aquifer will have larger radius of influence as compared to unconfined aquifer, and also it is said that it is larger for the higher transmissivity और ट्रांसमिटिविटी करके हमने एक देखा था, कोएफिशिएंट ऑफ ट्रांसमिटिविटी और ट्रांसमिसिविटी, देन दोज विथ लोअर ट्रांसमिसिविटी। अब ये क्या है ट्रांसमिसिविटी? T is equal to K into B is the capacity of an aquifer to transmit water through its entire thickness, है ना। K यानी कांस्टेंट है, कोएफिशिएंट ऑफ परमिएबिलिटी, और B यानी थिकनेस ऑफ द एक्वीफर है। द ट्रांसमिशन, और इसकी और एक डेफिनेशन है जो हमने देखा था, may be defined as the discharge through the aquifer of 1 meter width under a unit hydraulic gradient. It is the discharge through the aquifer who has got 1 meter of the width and the hydraulic gradient of 1 यूनिट हाइड्रोलिक ग्रेडियंट, ऐसे हमने दो, लेकिन ये basically the transmissivity or the coefficient of transmissivity shows the property of the aquifer to transmit the water, how much permeable the aquifer is and how much quantity of water is available. The difference measured in the vertical direction between the initial water table, the difference between the initial water table or the piezometric surface in confined aquifer एंड इट्स लोअर्ड लेवल, वेल में की जो लोअर्ड लेवल है, ये दोनों में का जो डिफरेंस है ड्यू टू पंपिंग एट एनी लोकेशन विद इन द रेडियस ऑफ इन्फ्लुएंस इज कॉल्ड एज ड्रॉ डाउन एट दैट लोकेशन. एक टर्म हमने और समझ लिया, ड्रॉ डाउन, जिसको हमने ओपन वेल में डिप्रेशन हेड करके बोला था. तो व्हाट इज द ड्रॉ डाउन? ड्रॉ डाउन इज नथिंग बट द डिफरेंस in the original water table or original piezometric head and the water level into the well, which is being down due to the pumping within the radius of influence. यानी ये जो radius of influence अभी कैपिटल R में देखा, ये radius of influence में और भी वेल है. जैसे ये पहले तो हमारी सेंट्रल वेल है, बाजू की जो दो टेस्ट वेल है जिसको हम इमेजिनरी करके बोल रहे हैं, ये टेस्ट वेल का भी यदि ओरिजिनल वाटर टेबल और द वाटर लेवल इनटू द वेल, इसका डिफरेंस यदि हमने देखा S2, ये हमारी मेन वेल में वो है SW, और जो आउटर वेल है जो एट ए रेडियस ऑफ R1 पे है, वहां पे है ये जो difference in the water table and the water level into the well as S1. So S1, S2 and SW are the drawdowns. Very important, huh? Drawdowns at that location. But again, the important is within the radius of influence. Radius of influence क्या है हमने समझ लिया है. It is the outermost part of the cone of depression. Now well yield. Yield we have very nicely earlier understood. Well yield is again yield is nothing but the quantity of the water or the volume of the water discharge either by pumping or by free flow per unit time. Maybe per minute, per second, per hour. Okay, cubic meter per second, cubic meter per minute, cubic meter per hour, cubic meter per day is called as the well yield. ओके, एखादे वेल में से एखादे आवर में, एखादे मिनट में या एक दिन में जितना पानी हम निकाल सकेंगे पंपिंग से, उसे कहते हैं वेल यील्ड. As I have told you, I will be showing this sketch again and again. Okay, while listening me, you concentrate on both of these sketches, the cone of depression and regarding the this drawdown of the central well SW, S2, S1, H1, H2, HW, R1, R2, etc. Now the well yield अभी हमने देखा, that is the quantity of water that has been taken out or that is available through the well per unit time. तो ये जो वेल यील्ड है, वेल यील्ड पर यूनिट ड्रॉ डाउन, यानी 1 मीटर यदि पानी वेल का नीचे जाता है तो ये जो वेल यील्ड पर यूनिट ड्रॉ डाउन इन द वेल इज नोन एज स्पेसिफिक कैपेसिटी ऑफ द वेल. एक बहुत नई टर्म हमने समझ लिया कि स्पेसिफिक कैपेसिटी ऑफ द वेल is nothing but the well yield per unit drawdown. Okay, drawdown we have just understood. It is the difference between the original water table and the water level into the well within the radius of influence. कोई भी well, main well at the center or the adjacent wells, उसको हमने बोला drawdown. तो ऐसा पर यूनिट ड्रॉडाउन होने के बाद में या पर यूनिट पानी नीचे जाने के बाद में उसके समय में, उतने समय में या उतने ड्रॉडाउन के लिए जो वेल यील्ड है, पानी जो निकाल रहे हैं पर यूनिट ड्रॉडाउन इन द वेल इज नोन एज द स्पेसिफिक कैपेसिटी ऑफ द वेल. So you must have understood the concept of cone of the depression. It is formed due to the pumping of water through the well. So as this pumping is continued, means this pumping is uninterrupted, it is not broken, then what will happen? This cone of depression, initially if the water is just at 1 meter below the original water table, then the cone of depression will be small. The radius of influence will be small. But as the water level goes below and below, the radius of influence will go on increasing. With the depression, increase in the depression head, this cone of the depression will go on increasing till the pumping rate is balanced by the recharge rate. ये कोन ऑफ डिप्रेशन कब तक नीचे जाएगा? कि जब तक हमारा पंपिंग तो चालू है, लेकिन पंपिंग रेट जो है, यानी समझो क्यूबिक मीटर पर सेकंड, क्यूमेक्स में यदि पर सेकंड यदि हम पंपिंग रेट कर रहे हैं और क्यूबिक मीटर पर मिनट, तो जितना पानी निकाल रहे हैं उतना ही पानी अंदर आ रहा है. ऐसी जब सिचुएशन आएगी तब तक के ये कोन ऑफ डिप्रेशन नीचे जाता रहेगा. And when the pumping and the recharging rate are equal or balance each other, a steady or equilibrium condition exists, and then there is no further drawdown with continued pumping. So when this drawdown or this depression head reaches to certain level, water level into the well reaches to certain depth, such that the pumping, that is the water taking out rate, and the recharging, that is water coming into the well, both these rates, when they are equal, when they are balanced, then there will not be any further drawdown, or there will not be any further decrease into the depth, decrease into the water level into the well. This is called as the equilibrium condition. Okay, when the outflowing water is equal to inflowing water, and when the drawdown or the depression head is now constant, is called as the condition of equilibrium. And at this condition of equilibrium, from the well hydraulics point of view, because we want to learn the how the water enters into the well, what is the rate of the recharge, etc., from the fluid mechanics or hydraulics point of view. Then at this stage, when the equilibrium condition exists, we say that at this condition, the rate of the flow of water into the well is steady flow. Okay, it is the steady flow. Maybe uniform flow, maybe non-uniform, but steady flow is there. Okay, you all know the steady flow, unsteady flow, uniform flow, and non-uniform flow. You must have learnt in your fluid mechanics. So, to derive the equation for finding the incoming discharge Q for the steady radial flow, some assumptions are being made. We'll try to understand those assumptions. The flow is horizontal. The flow which is entering into the well is horizontal and uniformly distributed in vertical section. है ना, ये जो फ्लो है वेल के पूरे all along the diameter of the well, the water is coming horizontally into the well and it is uniformly distributed over the vertical section. यानी जैसे जैसे हम नीचे जा रहे हैं तो यूनिफॉर्म पानी दोनों वेल के all along the perimeter, circular periphery से आ रहा है. The velocity of flow is proportional to the tan of hydraulic gradient instead of the sine of hydraulic gradient. ये जो कोन ऑफ डिप्रेशन है इसका जो स्लोप है, to that slope the velocity is proportional. Velocity is proportional to the tangent of the hydraulic gradient, because this cone of depression line shows the hydraulic gradient, that is the falling of the hydraulic energy line. The above two assumptions are called as the Dept Forschmeier assumptions. है ना, एक बार एग्जाम में पूछ सकते हैं what are the assumptions, then you should be, what are the Dept Forschmeier of assumptions. So you should be know these two assumptions. There are further assumptions, 3-4 assumptions. The well is pumped at constant rate is one of the again assumption. The well fully penetrates into the aquifer. This is one of the assumption. The aquifer is homogeneous. यानी जो भी एक्वीफर है, एक्वीफर यानी क्या है, फिर से जियोलॉजिकल फॉर्मेशन है. जियोलॉजिकल फॉर्मेशन में क्या है, सॉइल है. तो जो भी सॉइल है अवेलेबल इनटू द एक्वीफर is homogeneously distributed. It is isotropic, again a property of the homogeneity and crystallinity, horizontal and infinite and of infinite extent. Water is released from the storage into the aquifer in immediate response to drop in water table or piezometric surface. ये जो वेल है, ये वेल में पानी इमीडिएटली आता है जैसे वाटर लेवल इनटू द वेल गोज डाउन, या वेल में का स्टोरेज धीरे धीरे जैसे कम होते जाता है, तो वैसे वैसे एक्वीफर में से मे बी ए कन्फाइंड मे बी अनकन्फाइंड एक्वीफर, the water will be supplied through this aquifer uniformly as there will be drop in the water table for the unconfined aquifer, or there will be drop into the piezometric surface for the confined aquifer. So with all these assumptions we will move further. The first, there are two derivations we will be trying to understand. They are very simple, not difficult with this knowledge of the depression head, etc., or the drawdowns and the cone of depression. The steady radial flow to a well in an unconfined aquifer. दोनों के ऊपर में न्यूमेरिकल आते हैं, भला डिफिकल्ट नहीं है. शुरू में थोड़ा सा समझने को अभी थोड़ा ये लगे तो we will have a revision in our next lecture. Try to understand, go through this through your notes, या ये लेक्चर में आपको इमीडिएट डालता ही हूँ इसका रिकॉर्डिंग, है ना. You don't go through the recording, I have found. The steady radial flow to a well in an unconfined aquifer. First we'll be trying to find out the discharge, and then the steady radial flow to a well into the confined aquifer will be finding. है ना, सिमिलर है दोनों. सिर्फ अनकन्फाइंड एक्वीफर में क्या है कि इसका जो टॉप है अनकन्फाइंड एक्वीफर का वो हरदम वाटर टेबल रहता है, और जो बॉटम है वो इम्परमिएबल स्ट्राटा रहता है, ताकि इसके ऊपर में पानी जमा होता है इन द फॉर्म ऑफ द वाटर रिजर्वायर which we call as the unconfined aquifer. Okay, so the flow system around a pumped well in an unconfined aquifer with an initially horizontal water table is shown in this figure. Okay, I will be showing this figure therefore from the first slide of today's lecture, because you should have that imagination, and I have also explained you. The thickness of the aquifer is capital H, है ना. जो वाटर टेबल की टॉप लेवल जो है वहां से लेके तो जो इम्परमिएबल स्ट्राटा है, वहां तक के जो है तो वो एक्वीफर की डेप्थ या हाइट रहेगी या थिकनेस रहेगी. सो थिकनेस ऑफ द एक्वीफर इज कैपिटल एच, एंड दिस वेल अंडर कंसिडरेशन, अंडर स्टडी, ये फुल्ली पेनिट्रेट्स इनटू द एक्वीफर, है ना, ये तो हमने एजम्पशन में ही लिया है. If the water is now pumped out at a constant rate from the well, the cone of depression will be formed. A gradient in the water table towards the well is created, which results in a depressing form of the water table called as the cone of depression. After sufficiently long time, यानी पानी पंपिंग चालू ही है और ऐसा काफी समय होने के बाद में, when the contribution from the aquifer to the well is equal to rate of pumping, that is the equilibrium condition, the shape of the cone of depression remains fixed in the space and will not change any further at this point. The flow is said to be steady. है ना, हमें क्या करना है? We want to find out the equation of the discharge which is coming into the aquifer when the flow is steady. है ना, हमारे जो सिलेबस में है वो स्टेडी फ्लो तक ही हमें सीमित है. अनस्टेडी फ्लो, टर्बुलेंट, नॉन टर्बुलेंट वगैरह बाकी नहीं है. थोड़ा थोड़ा इंट्रोड्यूस किया है. सो व्हेन द वाटर फ्लो इनटू द वेल फ्रॉम द एक्वीफर will be steady when the water is being pumped out through the well, that is the rate of the pumping of water into the well and the rate of incoming of the water into the well will be same. That is when this cone of depression will no further go down. Okay. Initially the cone of depression has got a smaller radius of influence, but as the water level deepens down, goes down and down into the well, the cone of depression will go on enlarging, will go on becoming large and large. Its radius of influence will increase, and this continues till the rate of outflow from the pump and the rate of inflow from the aquifer, both this rate of the water will be equal. At this point, this cone of depression will regain a constant shape. फिर वो नीचे भी नहीं जाएगा और ऊपर जाने का तो सवाल ही नहीं. At this time, the flow which is coming into the well is called as the steady flow. And the decrease in water level at the well is called as the drawdown, that we have seen very well. If the drawdown is small compared to the thickness of the aquifer, the streamlines of flow to the well may be assumed to be horizontal. ये जो drawdown है ये बहुत कम है. Drawdown यानी हमने पढ़ा है कि ओरिजिनल वाटर टेबल और वेल की जो पानी की लेवल है इसके बीच में का जो डिफरेंस है, that is called as the drawdown. If this drawdown is very small, बहुत कम है, और ये एक्वीफर का थिकनेस भी बहुत कम है, एच जो है, तो फिर ये ज्यादा कोनिकल नहीं दिखेगा, एज इफ द वाटर इज एंटरिंग हॉरिजॉन्टली, ऐसा ही दिखेगा. द ड्रॉडाउन इज स्मॉल कंपेयर टू थिकनेस ऑफ द एक्वीफर. द स्ट्रीमलाइंस ऑफ फ्लो टू द वेल मे बी एज्यूम्ड टू बी हॉरिजॉन्टल. As again the same sketch I have repeated. Now the steady flow condition has reached, that is the rate of the pumping and rate of inflow is same, and the cone of depression has regained a constant shape. At this condition, the depth of flow at any radial distance r from the well is h. है ना, ये यहाँ पे एक it is assumed that at any distance r, must be watching on your slide, at any distance r from the center of the well, the depth of water is shown by small h. Okay, so at any radial distance r from the well, the depth of the flow is h, and the area of flow at this section is 2 pi r h, है ना. यहाँ पे क्या है, यदि प्लान से हम देखते हैं तो ये सर्क्यूलर है, ये सर्कल का रेडियस है स्मॉल आर. तो नेचुरली इसका जो पेरीमीटर होगा वो होगा ट्वाइस पाई आर, है ना. इसका जो पेरीमीटर है एट ए डिस्टेंस ऑफ स्मॉल आर, द पेरीमीटर विल बी ट्वाइस पाई आर, और इसकी हाइट है h. देयरफॉर द एरिया ऑफ द फ्लो, यानी जितने एरिया में से इसके अंदर पानी आ रहा है वो एरिया सिलिंड्रिकल एरिया है, और वो सिलिंड्रिकल from all the periphery of the well water is coming inside the well, assuming that there is a cylinder which has got the radius r and which has got the height h. So the area of flow, inflow from the aquifer to the well at this section, which is at a distance of r, will be twice pi r, that is the perimeter of this assumed surface of flow, and h is the height. So therefore the area will be twice pi r into h. Now as per the Darcy's law, the velocity v is equal to k into I. K is the coefficient of permeability and I is the hydraulic gradient. Since the tangent of the water table is taken as the hydraulic gradient, हमने assumption में किया है, the tangent of water table is taken as hydraulic gradient, the velocity at this section becomes k, that is k into dh upon dr. ठीक है. यानी ये जो कोन ऑफ डिप्रेशन है, इसका जो, इसको यदि हमने टेंजेंट लिया, एक आधा टेंजेंट निकाला, तो वो टेंजेंट का जो स्लोप है वो स्लोप जो रहेगा दैट इज डिनोटेड बाय द dh, यानी थोड़े थोड़े स्मॉल, यदि हमने उसके डिस्टेंसेस लिए, स्मॉल हॉरिजॉन्टल डिस्टेंस एंड स्मॉल रेडियस, then it will be dh by dr. So therefore the velocity is equal to k into dh by dr, and then discharge is given by that Darcy's formula, area into velocity. Area we have found out twice pi rh into velocity is k into dh by dr. So discharge is equal to q into twice pi rh k into dh by dr. Okay, so this equation can be rearranged, and we could see that h into dh is kept on one side and all the remaining values are taken on this side. So therefore h into dh is equal to q upon twice pi k into dr by r. And if we integrate this equation, because we have taken this r and h are the variable radius and variable heights or depth of water into the aquifer, for finding out the discharge by integrate. Now we will integrate this equation within the limits. If there are these two observation wells, two test study wells or study wells you can say, at a distance of r1, has a drawdown of s1 or has a depth h1, at a distance of r2 has a drawdown of s2 and the height of water is h2, and this is integrated between r1 and r2 and h1 and h2. So integrating between h1 to h2 hds and r1 to r2 dr by r, the integration, after integration we will get h1 square minus h2 square divided by 2, which is equal to natural logarithm r1 upon r2, or q is equal to pi into k, again rearranged, h1 square minus h2 square log of the r1 upon r2, where h1 and h2 are the water levels into the two observation wells located at a radial distance of r1 and r2. है ना, मैं इसलिए आपको पहले से वो समझा रहा हूं कि ये क्या है भाई, दो वेल्स, ऑब्जर्वेशन वेल्स और टेस्ट स्टडी वेल्स यू कैन से. लेकिन वर्चुअल वेल्स, only to find out the discharges. The radius at which the cone of the depression just commences is known as the radius of influence, that is the capital R, outermost radius denoted by R, where the cone of depression starts. If the radius of influence is known, the discharge can be computed even in absence of the observation wells using boundary conditions of the well. कैसे निकालते हैं अभी नेक्स्ट स्लाइड में हम देखते हैं. ये तो इक्वेशन कैसे डिराइव किए ये मुझे लगता है आपके ध्यान में आया होगा. फिर से आप पढ़ेंगे, फिर से आज का लेक्चर वीडियो लेक्चर देखेंगे तो आपको और अच्छे से ध्यान में आएगा. तो द स्टेडी फ्लो डिस्चार्ज टू द unconfined aquifer well or well into unconfined aquifer Q is given by pi into K H1 square minus H2 square logarithm of R1 upon R2. R1 and R2 are the radius of the observation wells from the well under study, main well. R1 is greater than R2 and H1 and H2 are the depths of the water. Again H1 is greater than H2. R1 is greater than R2, H1 is greater than H2. But in absence of this H1, H2, R1, R2, we don't have these values or we don't have the observation wells. But if we know the radius of influence, R, capital R, then we can rewrite this formula, that is 9.34 wala jo formula hai, in the form of capital R, capital H, HW, that is this HW and SW. In this form we can write down. How? Let us see. So pi Q is equal to pi into K. H1, instead of H1 we can write down capital H square. Instead of H2 we have written the depth of the water into our main well or well under study, HW. So H square minus HW square log of capital R, and RW is the radius of our well under study. है ना. ये स्केच में हमने देखा कि RW जो है, RW is nothing but the radius of the well under study. ये जो well है, ये well की जो radius है वो RW है. So putting this we can find out the discharge, steady state discharge, if we know the radius of influence and corresponding depth or thickness of the aquifer. So where HW and RW are the water level in the well and radius of the well respectively. Now this equation can be further modified as, but K, that is K into H square minus HW square can be rewritten as 2 times 2 से मल्टीप्लाई किया हमने और डिवाइड भी किया 2 टाइम्स से, तो यहाँ पे कैंसिल हो जाएंगे, लेकिन अभी लिखा है हमने 2 टाइम्स K अपॉन 2, as this is H square minus small h W square, it can be written as H minus HW into H plus HW, H minus HW into H plus HW. Here it is written H plus HW into H minus HW. बाकी तो K वैसा ही है, 2 से सिर्फ मल्टीप्लाई और डिवाइड किया है. H minus HW is nothing but the drawdown in the well itself. H minus HW is SW. Okay, SW, that is the drawdown into the well under observation, under study. And H plus HW, that is H plus HW divided by 2, can be taken as the average thickness of the aquifer. Aquifer का जो thickness है वो हम ले सकते हैं. तो ये जो इक्वेशन है ऊपर में लिखा, उसमें जो K इंटू H स्क्वायर माइनस HW है, इसको हम फिर से QK, we know that coefficient of transmissivity T is equal to K into B, that is the thickness of the aquifer B multiplied by coefficient of the permeability K. तो ये अभी कैसा लिख सकते हैं हम? K H1 plus HW divided by 2 is the thickness T. Therefore, T into K is the thickness B. H plus HW we divided by 2. We denote the thickness of the aquifer by small b. So B into K is nothing but coefficient of transmissivity T. So therefore 2 times T into H minus HW is the drawdown, which is SW. So therefore K into H square minus HW square can be rewritten as 2T into SW, where T is the average transmissivity and SW is the drawdown in the well. So the discharge can be now written as twice pi T, coefficient of transmissivity, into drawdown into the well, log of the radius of influence and radius of the well. Generally, the radius of influence is taken as 3000 SW, that is the drawdown into the well, square root of the K, where SW is in meter and K is in meter per second, that is the coefficient of permeability. So all these above equations can be used to estimate the yield from the well when the hydraulic conductivity is known. That is, K is known, coefficient of permeability, or hydraulic conductivity also it is called as, or to estimate the hydraulic conductivity of the aquifer if the discharge from the well is known. So both these equations, that is this one, I into K into H1 square minus H2 square log of R1 upon R2, this is 9.34, and this equation, that is Q into twice pi T into SW log of R upon RW. Both these equations can be used to estimate the yield from the well, that is discharge from the well, when the hydraulic conductivity, that is K, coefficient of permeability, is known, or by knowing the discharge we can find out the hydraulic conductivity of the medium, of the material of which the aquifer is produced. Both these equations fails to describe accurately the drawdown curve near the well because the streamlines there are marked curve with large vertical flow components contradicting to assumptions. यानी जो हमने assume किया है कि flow horizontal आता है, ऐसा नहीं होता, practically वो curve में आता है, लेकिन वो हम उसके ऊपर उतना ध्यान नहीं देते. Another serious drawback of this equation is that true steady state equilibrium condition required for its applicability occurs only after very long pumping period because of the low velocities of the groundwater flow. These are the two drawbacks of this equation. We will stop here. The remaining part